So now we have last lecture we have discussed the idea behind the scattering, how to do the scattering, theory of scattering. So we have modeled our scatter as a potential. So we write the total Hamiltonian to be H0 plus 2. So this is essentially the free particle. And this describes our scatter. Okay, so we need to figure out the solution of this very problem that now discusses in the essence of the okay. So what is our goal? Okay. So I am having, let's say, these three particle states is 0, they are the momentum states. So this is simply equal to p square by 2. So this is the eigenvalue. Clear? So I will describe, instead of writing p directly, but I'll use phi to be the eigenstate of this set. Like this, okay. So now our goal is to solve this Schrodinger equation. So I need to solve this equation. X psi is equal to some, let's say, E psi. Clear? You got my point? We have to solve this very equation. Okay? Or, so what this is exactly? So it is H0 naught plus this V psi, that's equal to E psi. Okay? So we have to solve this equation for psi such that, okay? So there is a condition such that if this V tends to 0, that means if there is no potential, this psi goes to what? Phi. Clear? Look here. So if I put V equal to 0, so then the psi is actually the eigenstate of H naught. That is simply the phi. We have considered phi to be the eigenstates of H. Clear? Okay. So now how to solve this kind of equation? Huh? Okay. So we have to solve this kind of equation. So there is a okay. So I will write this equation. Okay. So this very equation. Let me write it in this fashion. Okay. So I will write it like this thing. E minus, let's say, H naught, clear? Psi, that is equal to V psi, clear? So I can put it in this fashion. Now what I will do, so I will work out the solution of this way in this equation, clear? So I will write this thing. Let's suppose, okay? Let's suppose this is the solution. This psi is equal to, so you do, since this is an operator, so this is an operator, divide this operator on this very side. So like this thing. H naught, clear? So then you are having this V psi. So let me put some constant here, what we call as a phi. So let's decide is this operator being singular at E equal to H naught. Clear? So everybody got it? So okay, so look here. So what I have done, so I can calculate this psi from this very equation. How I can calculate this psi? So just divide this operator on this side. So that means I'm actually acting an operator E minus H naught inverse. So that is this operator. Okay. So then you are having V psi. So you are having psi on both sides. So then you have to make, you have to solve this recursively. You put the value of psi here, then again psi. The way we have done the Dyson series or Dyson sum. Clear? Okay. Now the point is here, what is our boundary condition? if v tends to 0, then psi must go where? Phi. So forget about this very operator here. It's singular in nature. It is singular when E is equal to H naught. When some eigenstate becomes actually have the same energy, E is equal to H naught. Clear? When this vanishes, then you are having a singularity. Let's forget about this for the time. If I take E tends to 0, so what happens to psi? No, here in this equation. So if I take V tends to 0, this goes to 0. Clear? So for that matter, what I will put? I will put a term, okay, phi. Now this makes sense. So if I take now V tends to 0, then psi tends to phi. Got it? So it means this solution accepts the boundary condition. So it is inconsistent with the boundary condition. Got it? Okay. Now we need to check whether this yields me, whether this really is the solution of that equation or not. Okay? So I have to figure out the solution of this very equation. Okay? So I need to check, is this the solution to that equation or not? Okay? Okay, how to do it? So let's operate let's operate E minus H naught. Let's take E minus H naught. Convince yourself about this thing. So, sorry. I'll take this psi is equal to this phi plus 1 minus. So let me take this as a solution. So now there is a problem. So there is a singularity coming from where? This very denominator. How to remove this thing? Okay. So that I will put directly here. How to to do it. So I will explain it later when I take the Green's functions. Okay. So once you do the Green's functions, so then I can tell you what. Okay, the way I will remove these singularities here. Okay, so it will be clear from the Green's functions. Okay, so it will not be clear from this very point. Okay, so the point is here, what I will do, since E represents me the energies, clear? So, okay, so these energies are here real quantities. So what I will do is to remove the singularity here, I will simply complexify this energy. The poles, let's say if you are having the axes, let's say the energy plane, so I will complexify my energy plane. So you are having this energy real of E, so imaginary of E. Clear? So what I will, if you look at where are the poles? Poles are on the real axis. Clear? So let's say you are having two poles. Let's assume. Okay. So let's assume you are having two poles. Both are on the real axis. Got it? So what I am trying to do, I will simply shift the poles to the complex plane by an infinitesimal amount. Okay. So in other words, I will shift them here. Like this, and I can shift this here or the above, like this. By the infinitesimal amount. What it will do, it will simply give me the okay. So it will simply remove the singularity or the singularity along the real axis. Okay. So if you remember when we were doing the poles of a S matrix, okay, if you turn it out to be a complex number. What was the interpretation? The complex part gives me the lifetime of that particle. Clear? Okay, since so if this is some infinitesimal amount in the complex plane, so it means it is still having the infinite lifetime, because it is what? Epsilon tends to 0, it means still infinite. When I take the finite epsilon, let's say, although very small quantity, it means I am giving some small, a damping effect to that particle state. Got my point? So at the end, we can remove this damping factor. Samajh? So here it is very ad hoc in nature, because I have not explained why to do so. Once I will take the Green's functions, it comes actually from the Green's function method, solving a differential equation. Okay, so here I have not solved Green's function in detail. So what I will do to remove that, so I will put some I epsilon, some small amount. I am shifting the poles either to the Okay, lower half plane or to the upper half plane. Got it? समझ रहे हो? So now the singular nature of this very operator is being removed. Okay? So if you see, this is a cat equation. Okay? So you are having a cat. What we are trying to figure out, this psi is a solution of our equation, and it appears on the right hand side as well. So you need to solve this in a perturbative fashion. This kind of equation. We call this equation as Lippmann-Schwinger equation. Okay? Got it? Okay. So let's move ahead. Okay. So what I will do, so this is actually independent of a basis. I have not chosen any kind of basis, whether I am doing my calculation in the coordinate basis or calculation in where momentum basis whatsoever. I have not chosen any basis. This is actually the basis independent representation of the Lippmann-Schwinger equation. Okay, so now let's do our calculation in the coordinate basis. That means we are doing in the real space. Okay, so where we define a wave function. Okay. Okay, so what I will do, I will take a cat x and project this equation on this cat x. So this defines me the state vector describing the position of a particle. Okay, so if I take, let's say, x, so it will define me what? State vector defining the position of a particle. Clear? So x will specify, so me the coordinate. In other words, if you are having a coordinate operator x, so it will simply give you the coordinate of the particle x. Clear? So this x can be, so this is a these can be the three coordinates x, y, z. It can, okay, if you think in one dimension, it is simply the x coordinate. If you think this cat defined in three dimensions, then this x will simply give you x, y, z, or the vector x. It will simply give the position vector of the particle. Okay. So now let's choose this base. Okay, so these satisfy this kind of relations. Okay, x minus x prime. So in three dimensions, and dx x. So that's equal to 1. Since this is complete now, okay, so it forms a basis. Okay. So now let's project that equation on this cat x. So it means you will multiply on left by this cat, this brass state x, okay, on this side like this thing. So that's okay. So when I put plus minus epsilon here, I will put a plus minus here sign. Clear? So plus minus epsilon when I'll put a plus minus signs on the cat this side. Okay. So to distinguish between two types of states, one state that will be having a plus I epsilon prescription, another will be having a minus I epsilon prescription. Clear? So we'll understand in a moment what exactly this psi plus minus will yield me. Okay. So let's take it. Psi plus minus. So it is something x. This is 5 plus, okay, like this. Epsilon psi plus. Okay. Now tell me, if you are having x psi, how you write it as psi of x. Got it? So now it is your wave function, coordinate representation of the state vector psi. Okay. So this I can write as or psi plus minus x. That's equal to, so this will be simply phi of x. Okay. Plus. So now, so what I will do, I will introduce, so this is x. So here I will introduce the completeness condition, this x. Okay. So like this thing, 1 divided by e minus h naught, okay, plus minus I epsilon integral of let's say dx prime x prime x prime v, okay, psi plus. So if you are not able to understand it, just stop me, yeah? Okay, you got it? So what I have done, since you are having a v here, and these are two operators, in between these two operators I am inserting a completeness relation. Clear? So it is simply multiplying by the identity, so that I will be having a vector, this potential defined like this thing, and this operator is defined in the coordinate base x, this operator and x prime. Clear? Okay, so you are having this as phi of x plus integral of dx prime x, okay, plus minus I epsilon x prime. So this is x prime v psi. Let's call this equation. Clear? So now what I will do, I will try to evaluate this very part. So let me define the quantity. Okay, g plus minus. Okay, so this x prime is equal to. So I will introduce some numbers here. Okay, like this. Let me define this thing, extra square by 2m. Okay, then you are having this x 1 divided by e minus h naught plus minus I epsilon x prime. Clear? So I have multiplied by which factor? Extra square by 2m. So that means I need to multiply this here by, okay, 2m by extra square and extra square by 2m, that will cancel. Clear? So you should keep it in mind. So, okay, so this g plus minus we call as a Green's function. Forget about it. So I will tell you later on what exactly these things mean. But I will just represent this function by this g. Clear? To simplify things. Okay. So how to evaluate it? Now I know this h naught is actually p square by 2m. Clear? So it is simply the free particle Hamiltonian. So what are the eigenstates of the free particle Hamiltonian? So these are the momentum eigenstates. Got it? So in order to, okay, so but this is actually the matrix element between, in matrix element in the coordinate space x and x prime. Clear? So this operator is defined for the momentum states, and but I am having what? The coordinate space representation here. So I will convert this object into the momentum space representation. Clear? So for that matter, what I will do, I'll introduce, let's say, the momentum eigenket such that this p prime, it is equal to delta 3 p minus p prime. So I'll put a vector notation here to just make it clear. These are, we are doing the calculation in 3 dimensions. Okay, so this is your vector and similarly you are having like this thing. Okay, so d3p, okay, this p that's equal to identity. Okay, so you can, okay, so you can rewrite this p prime in this fashion. So I will write it as like say dx, then I will write p prime x. So I have inserted actually this relation. So it is delta 3 p minus p prime. Clear? So I inserted a completeness condition here. Got it? So that if you see, this is simply the normalization of the plane waves. So what is this xp? Yesterday we wrote it. So it is e raised for I p dot x by h cross divided by 2 pi h cross 4 3 by 2. Clear? So in 3 dimensions, this is, if it is in 1 dimension, it will be simply 1 by 2. Clear? Okay. So now let's convert this object into the space, momentum space. So we can write therefore the g plus minus xx prime So it is equal to extra square by 2m. So let me write x, and I will insert one condition here. Let's write dp prime, p prime, p prime like this thing. Then you are having this operator e minus. Okay, so it is p square by 2m plus minus I epsilon, because h naught is p square by 2m. Clear? And then you are having this. Let me write here on this side integral of dp double prime, p double prime, p double prime. Okay, so on then you are having this x prime. Yes? Any question? Okay. So everybody is following it? I have inserted two identities on the either both sides of this very operator. Clear? Okay, now look here. So I will take this thing extra square by 2m. So you are having dp prime. So you should put actually, okay, so it is d3p here. D3p, because we are in 3 dimensions. Okay, it is d3p. d3p double prime. So now look here, you are having x and p prime like this thing, x and p prime. Okay, since this is a Hermitian operator, p square by 2m is a Hermitian operator. It can act both left as well as right. When p square acts on p prime, what it will give me? The eigenvalue. So that is simply p prime. So it will be something like this: e minus p prime square by 2m plus minus I epsilon. Okay. So what remains here? P prime and this p double prime. So you are having p prime, p double prime. Then you are having this objective p double prime, x prime. Clear? Got it? Okay. So what this object is? So this is delta 3 p prime minus p double prime. Okay. So then you integrate over either p double prime. Let's integrate. Okay. So integrate over p double prime. This p double prime will be replaced by p prime. Clear? Okay. So it's equal to then. So extra square by 2m integral d3p prime. Okay, you are having this xp prime. Okay, then you are having that. Okay, so when p double prime will be replaced by p prime, so you are having now p prime x prime. Okay, divided by this e minus p prime square by 2m plus minus I epsilon. Clear? So now what is xp prime? So xp is this object. Clear? Okay. So it's equal to extra square by 2m d3p prime. So it is e raised power, okay, I p prime dot x. Okay, so these are vectors divided by h cross divided by 2 pi h cross whole 3 by 2. Then you are having, this is actually the conjugate of this thing. Only p prime and only these are changed. Okay, so it will be simply e raised power minus I p prime dot x prime divided by h cross divided by 2 pi h cross 3 by 2. So 1 divided by, okay, so e minus p prime square by 2m plus epsilon. Okay, got it? So now we need to evaluate this integral in order to figure out this g plus minus x. Clear? Okay. So let me rewrite it. So you are having the g plus minus xx prime. So let's write. Okay, so let's redefine our variables. So I can write this. Okay, so let me write this e as extra square t square by 2m. Okay. Okay, so I'll put it this way. Okay, so there is an okay, so now look here, there is an integration over p prime and p prime exists here. So sure? Okay, so what I will do, also I will set, okay, let's set this p prime is equal to h cross q. Clear? So what I will do, I will set this p prime as h cross q, just rescale the variables. Okay, now look here, you are having p prime square by 2m it will be now extra square by 2m q square, okay? And E will be what? Extra square k square by 2m. So you can take extra square by 2m out. It will cancel out the factor extra square by 2m outside. Clear?
Yes, sir.
समझ आओ? So everybody, so you are having extra square k square by 2m. So extra square by 2m you take out, it will be like this. Now what happens to this thing? So when you take extra square by 2m out, it will be 2m by extra square epsilon. So since epsilon is very small, epsilon tends to 0, it will be 0. So you can, it will not change this thing. So it will be simply rescalar at this very point, but it is simple, again the infinitesimal amount. Okay?
Yes, sir.
Samashaman? Everybody got it? So I will not change epsilon to some another, I will put simply epsilon. Okay? Got it? Okay. So what we will get? Okay, and one more point. So you club these two factors. You are having p prime is here. It will be p prime dot x minus x prime. Okay. So you are having this g plus minus xx prime. Okay, so let me write it. So, and one more point, when I am taking p prime to be equal to h cross q, so is there any other factor that will cancel? Is there any other factor that will cancel out? There is an h cross q, is it? Is that true? There is an h cross raised to power 3 by 2. So there is that kind of factor as well. Okay, so let me write this as in this very thing. So it is h cross square by 2m integral d3q divided by 2 pi q. Okay? So, okay? Yes, 3 by 2 and 3 by 2. H cross q will cancel out because of this objective. Okay? So what you are having here, e raised power I p prime dot x minus x prime divided by, so you are having this h cross square k square by 2m minus h cross square q square by 2m plus minus I epsilon. Okay? Everybody? I have just read it here. So only this q, h cross, it will be h cross cube here, h cross cube here. So that I have cancelled. Okay, so now I will cancel this h cross square by 2m here. So you are having now like this, k square minus q square plus minus I epsilon. Got it? Okay. So anything more to it? No, it is epsilon. Clear?
Yes, sir.
Okay, so there is this. Okay, so it will be what factor? It will be simply q, because you are having p prime is actually okay h cross q. So to remove this h cross, okay. Okay, so let's do this very calculation. So let's evaluate it in the spherical polar coordinates. So how it will look like? So this is very important. Now look here. So you will see now, since there is an integration over q. So if let's say if I had put this epsilon equal to 0, there is no this epsilon. So you are having all the poles on the real axis. So it's very difficult to integrate on the real axis. So you cannot integrate directly on the real axis unless and until you shift the poles to the complex plane. Okay, so let's see. So I can write this thing 1 by 2 pi cube. So it is 0 to infinity q square dq. Okay, then I am having integration over 0 to pi sine of theta d theta. Okay, then we are having 0 to 2 pi d phi. Okay, so over the solid angle. So then you are having e raised power I q. So it will be simply equal to magnitude of x minus x prime cosine of theta divided by this thing k square minus q square plus minus I epsilon. Got it?
Yes, sir.
So since there is no phi dependence, you integrate over phi, you will get 2 pi. Clear? So you simply get 1 divided by 2 pi square. So that is equal to 1 by 4 pi square. Okay, then you are having integration over 0 to infinity. What I will do, I will simply change the sign. Here I will take minus out. Okay, like this thing. So I put a minus sign here. So in a moment you will see what I am doing. So it is 0 to pi sine of theta d theta, okay, e raised for I cube magnitude of x minus x prime cosine of theta divided by q square minus k square minus, so like this thing.
Yes, sir.
So this is very important, right? Got it?
Yes, sir.
So I have taken this because I am integrating over what? Okay, so let's integrate over first theta. Okay, so I'm sorry, I should have put this on this side. Okay, so let's integrate this objective first because this is having theta dependence. Then we'll integrate over q. Clear? So let's integrate it. Anybody can you tell me what is the integration here? Can anyone tell me what is integration? So simply put, let's say you put this value factor equal to some z. Got it? So let's put z is equal to some q magnitude of x minus x prime cosine of theta. What you will get? Dz is equal to, rather minus dz q. Just tell me. Just tell me. So it is sine of theta d theta, that will be equal to minus 1 divided by q x minus x prime dz. Clear? Got it? Okay, so now what are the limits of integration? So the limits of integration, what will be when you are having theta is equal to 0, z is equal to this thing. But there is a minus sign here, so I will interchange the two. So it is minus q, okay, x minus x prime, okay, and it will be q magnitude of x minus x prime. So it will be simply dz e raised for I z. Clear? Is it true? Okay. Huh? Got it? Everybody is following it?
Yes, sir.
Okay. So it is equal to e raised for I z. The first part will be x minus x prime minus e raised for, okay, so this very value minus I cube x minus x prime divided by, got it? Yes, there is a this factor, right? So you are having this factor. So q into x minus x prime. Okay, so it is equal to I times q x minus x prime. Everybody followed this integration? If anybody is not able to understand, just tell me, I will redo it. Okay, so now let's substitute this value here. Okay. Yes.
So it's not minus 1 by 4 pi square.
That's
So the integration.
minus
So 1 divided by 2 pi whole cube.
4 pi square.
No, no, sir.
Integration over 5 is 2 pi.
2 by 2 by.
Okay, 2 pi and 2 pi will cancel. What remains there? 4 pi square. Clear? And minus comes from here because I interchanged the minus here. Huh? Clear?
Yes, sir.
Huh? No, no, agreed? Okay. So you should not get confused. So I actually interchanged them. Okay, I have taken minus out. So to put it in this fashion. Okay, it is something integration over, let's say, dz z square minus a square kind of integral. So you are solving that integral. So therefore I can write this g plus minus. Okay. So g plus minus x x prime. So that's equal to minus 1 by 4 pi square. Okay. So since there is no integration over coordinate, you can take this x and x out. So and there is in this I sitting. So you can put in like this in 1 divided by I x minus x prime. So then you are having integration over 0 to q, 0 to infinity dq. You are having q square here, and in the denominator there is q. So 1 will go out. So now you are having this exponential e raised for q, okay, x minus x prime minus e raised for minus I cube, okay, x minus x prime divided by what? This thing, q square minus a square minus plus I epsilon. Okay? So this is very important, the minus. So that means one singular, so there are no poles. two poles, is it? Both are simple poles actually. You have to use the residue theorem to calculate this kind of integral. I will give you the poles. Okay, so why poles are actually situated. Okay, so you are okay. So I will not do the integral. So you have to do it, this integral. This is very simple. Huh? So it is 2 pi I sum of residues. Huh? But you have to choose only one plane. Huh? You either choose the upper half plane or the lower half plane. Got it? Okay, so you are having poles where q square minus like this thing, I epsilon that's equal to 0. So where are they? Q square is equal to k square plus minus I epsilon when you take it on the other side. So let's take this k square out. So it is 1 plus minus I epsilon k square. Okay? Got it? So what it is? So therefore q is equal to, when you take the root, it will be plus minus k root of 1 plus minus I epsilon k square. Got it? Now since this is a small quantity, you can make a binomial extension here. So that means q are equal to plus minus k. So this I can write 1 plus minus I epsilon 2 by k square plus epsilon square terms. So those are 0, essentially 0. Why are now the poles? So you are having two poles where like this thing, plus minus. So you can put epsilon by 2 k square as some, let's say epsilon prime. Okay, at the end of the calculation you put epsilon prime equal to 0. Got it? So you are having one pole at k plus I epsilon, another pole where minus k minus I epsilon. Got it? So these are the two poles, and you have to do now the integration by residue theorem. Got it? समझ आवा? So do that. So I will put the result in now. So if you are not able to do it, so I will give you the calculation. So the integral turns out to be the g plus minus x prime. It turns out to be minus 1 by 4 pi e raised power I k x minus x prime. This magnitude. So plus minus here, divided by x minus x prime. Okay. So this is actually the solution of Helmholtz equation. So let's forget those things. So this is our solution, g plus minus. Okay, so let's switch. Let's plug in this result in equation 1. Okay, got it? So everybody followed it. So what we will get? So which implies therefore I am having the psi plus minus x. So that's equal to phi of x. So minus 2m by h square. So the minus comes from here, and 2 by h 2m by h square comes from where? We have multiplied by the g h square by 2m. Correct? So integration over d3x prime. Okay, e raised power plus minus I k x minus x prime divided by 4 pi x minus x prime. Okay, then you are having this x prime d psi. So let's call it certification second. Okay, so this is a very important equation. Yes.
सर जब हमने वो एप्सिलॉन को वहाँ से निकाला था ना बाहर, वो h कट अपॉन 2 है, वहाँ पे हमने एप्सिलॉन को बोला था इट इज इनफाइनेटली स्मॉल, वी कैन राइट इट एज एप्सिलॉन. तो यहाँ पे हम नहीं कर सकते वो,
Just to, in order to differentiate between this epsilon and, so that you will not get confused.
सर हम नहीं, यहाँ पे हम इग्नोर नहीं कर सकते हैं आयोटा बाय 2 के स्क्वायर.
So no, you are writing not I. 1 divided by 2 epsilon by 2 k square is again small quantity. Clear? So that small quantity I have put at epsilon prime. So you can put there that 2m by h square times epsilon as some delta. Okay?
Yes.
Got it? So because this epsilon is immediate here, that is why I don't want to put epsilon here. Clear? So that you should not get confused. What's happening? Got it? Okay, so now let's try to interpret this equation what we have got. Okay, so that we'll see in a moment. Now the solution what we have obtained, for our scatterer. Okay, that is described by the potential V. Okay, so there should be an operator. So it consists of a solution, a plane wave. So phi of x represents me the incoming plane wave. Clear? Got it? So in the far off domain, we'll see in a moment that this very factor looks like as e raised to I k r divided by r, like this kind of factor. E raised to plus minus I k r by k r. Sorry, r. So it looks like this thing. So what kind of wave this is? So it's again a plane wave. It is a spherical wave. Okay, in 3 dimensions, this represents a spherical wave. So that means you are once the particle hits the scatterer, okay, or the incoming wave hits the scatterer. So the outgoing wave is what? So you are having two types of solutions. One corresponds to the plus. If you are having plus IKR, it's an outgoing spherical wave. Clear? If you take minus IKR by R, so that's an incoming spherical wave. So, but the boundary conditions what we have set, you are having an incoming particle hitting the scatterer. So then what will happen? So you are having only the outgoing waves. You measure the outgoing waves. You are not constructing the boundary condition where you will be having an incoming spherical wave going towards the scatterer. Got it? So we will discard psi minuses. Then I can have this the interpretation of this psi plus minus as. So psi plus will give me actually a wave representing the incoming and the scattering part of the waves. Okay, clear? Our psi plus will give me the incoming wave plus an outgoing spherical wave, and psi minus will give me an incoming wave plus an ingoing spherical wave. Okay, so I will discard this psi minus solution and we will work only with what? Psi plus, so that it is consistent with our boundary condition. Got it? Okay, so let's explore it a little bit further. Okay. Okay, so since there is a potential here sitting, we have not said anything about what kind of potential this is. We have just said our scatterer is represented by the potential. So let's assume our potential is local in nature. So it's confined to a given region. That means it's having a finite range. Okay. So let's assume. So we'll take this thing. Assume V to be local. That means we are having finite range potential that describes our scatter. Okay. So in coordinate space, so I write it like this: x prime V x double prime. Let's say so it is something V. Okay, so it will take like this x prime. So it will be a number now. Delta 3 x prime minus x double. The matrix elements. Okay, so this is completely local. That means this is localized to a given domain. Samajh aa? Okay. Now let's evaluate this way object. So I am having therefore this x prime V psi plus minus. For the time being, I will take both. Okay, so this I can write as like this: integration over dx double prime. Okay, x prime V. Okay, x double prime. So x double prime psi plus minus. Clear? And I know this is local, so it will be something dx double prime. So it will be vx prime delta 3 x prime minus x double prime. So it is clear. So now integrate over x double prime. So x double prime will be replaced by x prime. So it is simply vx prime. So x prime psi plus minus. Okay. Got it? Everybody followed it? Okay. So therefore we write. Okay. So we write this psi plus of x. We will take only now psi plus of x. Okay, you can write psi plus minus, it doesn't matter, but we'll work only with psi plus minus 2 by m h cross square integration over d3 of x prime e raised to plus minus I k x minus x prime divided by 4 pi magnitude of this x minus x prime. So it is simply v of x prime here, then you are having x prime psi. Okay, so these are actually the integral equations. Okay. Okay, so let's try to understand the content of this very equation, what I was saying. Okay, how it is actually an outgoing spherical wave. Okay, so let's try to understand it. So look here. So this vector x, what it defines? What it defines? So what is the direction of this x? Yes, it is the direction for the. So it gives me the what? So let's say if you are having some observation point P, so what x vector will be, how it will be directed? From the scatter towards this observation point. So it will simply give me the outgoing wave. So what about this x prime? What is this x prime? So let's say you are having, this is the region. Okay, so you are having a point, let's say it is a point O. Let's think it as an origin where there is an incident wave. Okay, I am having this as an incident wave. So let's write it as P is equal to H cross K, where K is a wave vector of this very wave. What will happen? So let's say I am having an observation point P that's very far away from this very scatter. That makes actually sense. Okay, so you are having this as x. Okay, so this x prime, since there is an integration over x prime, that means this x prime point exists within the region where there is a scatter. Okay, Samashyam? So when you integrate over x prime, it means you are integrating over the domain of the potential, domain of this very scatter. So let me write this scatter. So this is the point x prime. Okay. So then the difference between these two vectors is what? X minus x prime. Got it? Samashyam? So now let me write this. Okay. So in a typical setup, how we do things? So the detector which is positioned at P, it's very far away from the scatter. That makes sense. Clear? So if it is very near to the scatter, then I can't measure anything. Because I will be under the influence of the potential. What I want to do, I want to measure the scattering particles, okay, at a very large distance. Okay, so where there is no influence of this very potential. In that case, this x is very larger than x prime. So what I will do, let's define this r as, okay, this x, okay, magnitude of x. Let's write this r prime as the magnitude of x prime. Okay, so let's call this angle as alpha. Okay, so alpha is the angle between r and r prime. Clear? Okay, so what is our region? So r is very larger than r prime. So this is our domain. So now let's extend that x minus x prime. So I am having this x minus x prime. This I can write as what? So magnitude of x square, what is that? That's r square minus twice magnitude of x. That's r magnitude of x prime. That's r prime cosine of alpha plus magnitude of x prime square. So that is r prime square. Just the angle formula, cosine angle formula. Okay. So let's take r out. So you take r out. So what remains there? So it's 1 minus twice r prime by r cosine of alpha plus r prime by r whole square. Since our approximation is what? R is very large than r prime. So let's apply that. So it will be r. So this quantity is very small. This is very small. Okay. So this is smaller in comparison to this term, and this is smaller in comparison to this thing. Okay, I will retain only this very term. So it is something then 1 minus x raised power half.
Yes.
So how much is that? 1 minus half of x. Got it? So when x is very small, when magnitude of x is very small. Okay, so then I can write it as 1 minus, so it will be simply r by r cosine of alpha. Okay, got it? So what is that equal to? R minus R prime cosine of alpha. R and R will cancel out. So what I will do, I will introduce a unit vector, because cosine of alpha gives me the direction cosine between what? X and X prime, or between R and R prime. Okay, so I will introduce a unit vector in the direction of this R. That means in the direction of X. Clear? So let's define a unit vector. R is equal to vector R by R. Clear? So in other words, I can write this object as R minus, anybody? This unit vector R dot R prime. Can I write it? Can I write it? Magnitude of R unit vector is 1, and then you are having R prime cosine of alpha. Got it? Okay. So also, what I can do, so we can have this approximation as well. So can I write now this 1 minus x prime magnitude as approximately equal to 1 by r? Can I write it? Can I write it? Because what is, so it is simply 1 by r into this very factor, because r is very small. Huh? Can I write it? Okay, so this object is approximately 4. Now let's plug it in here. Okay, kx in q. It's q. It's q. Devash kunja gadbad karo. It's q. Okay, it's q. Okay. Awesome. Let's suppose to plug in these results. So what we will get? What is it? Huh? Okay, just tell me. So what you will get? So we'll take only now positive solution. Huh? So the positive solution turns out to be psi plus of x as phi of x minus 2m by h cross square. Okay, then you are having this d3 of x prime. So e raised power plus minus I q. What is this thing? It is r minus unit vector r. Okay, r prime divided by 4 pi r. Then you are having this v of x prime. Then x prime psi plus. Since we are interested only in the positive solutions. Okay, so let me use this kind of notation. So let me write k. Okay, so we will use k. Yeah? K is equal to p by h cross. Okay. So I want to remove this h cross here. Eh? So this h cross. Is there any h cross anywhere else? Is h cross anywhere else? So is there an h cross? There seems to be an h cross somewhere. Eh? Huh? There is some h cross. That's why if I put p is equal to h cross k, sorry. So let me write. Where is p? Huh?
Q. P is equal to h equal to q.
So have I done anything? So what is our last equation? So what we are using? So it is k, not q. So it is k, not q. K, it's k because we have integrated it. So it's k. So this is k. Okay. So let me use now. Okay, so this, okay, there is no problem. Okay, so let me use this object. So you are having this k. Okay, so k multiplied by r, then you are having this very factor k into r, is it? So k is the magnitude of the momentum vector. okay, or the wave vector. R gives you the direction in the direction of the scattering, forward direction. So let me define this simply as vector k prime. Clear? So I will define this simply as k prime. So now what we got? So this psi plus of x, I write it as phi of x minus twice m by h cross square, and there is 1 by 4 pi. So let's take this e, sorry, it is only plus because we are taking positive solutions. E raised for I k r by r. Okay, what remains inside? D3 of x prime e raised for minus, so it will be k prime dot r prime. Okay, v of x prime psi. Clear? समझ आओ? Huh? Okay, what is actually vector r prime? It's x prime. Huh? Is that true? So you can write this object. Okay, so since r vector r prime is same as vector x prime, so I'll put this as x prime dot. Huh? So that makes sense of this very equation. Now, do you think there is an outgoing? Okay, so this is an incoming wave. Apart from other factor, there is this kind of wave. E raised for I k r by r. So an outgoing spherical wave. Clear? Okay. So let me write it this way. So I can write it as in this fashion. So psi plus of x, that's equal to okay. So that is something equal to. So what is phi of x? E raised for I k x. Okay, so I will write it as e raised for I k x. Let's forget about the normalization constant. That's 1 divided by 2 pi h cross cube. Okay, so let's forget that kind of factor for the time being, because it's ultimately a plane wave. Plane, you don't need to do the normalization. So okay, so I'll put it as plus e raised for I k r by r and some f of k prime k. Okay, so wire the rest of, okay, so e raised for I k r by r, okay, and the rest will actually represent the amplitude of this very wave. Samashavan? You got my point? So what is our f of k prime k? So what is f of k prime k? Just tell me. So it is minus 2m by h cross square. So then you are having 1 by 4 pi integral, okay, d3 of x prime e raised for minus I. So why you are not writing I here? So it is I here. So I k prime dot x prime. So you are having v of x prime and x prime psi. Okay? Got it? Okay. So this I can write as, so minus m divided by 2 pi h cross square integration. Okay, so since this is actually in the coordinate space, okay, so I will write it this way. So you are having this vector k prime, okay, then you are having this potential v, then you write this psi plus. Okay, so let me show you. So insert, okay, so let's take this k prime, okay, v psi plus. So let's insert this completeness condition. So it is d3 of x prime, okay, k prime. Let's say you are having then this x prime, okay, x prime, and you are having this v psi plus. Okay, so what this gives me? So it gives me simply the plane wave e raised for minus I kx. Yes. So this is simply equal to d3 of x prime e raised for minus I k prime x prime. Clear? Okay, then you are having this x prime psi plus. So it is this thing. And you know this x prime v psi plus, because v is local, it will be simply v of x prime psi prime. This I have shown you. Huh? Clear?
Yes, sir.
समझ आया? So in other words, this very I can write this f of k prime k as. So memorize this very formula. Huh? Okay, so memorize these two formulas. Suppose if you are having a scattering problem, so the outgoing scattering wave is actually the superposition of two waves. One is the incoming wave plus an outgoing spherical wave. Huh? So the effect of the scattering is contained in this very term. Huh? and the magnitude of the scattering, okay, how much scattering has been occurred is given by this amplitude of the wave, f of k k prime. Clear?
Yes, sir.
So we'll calculate the scattering cross sections from this f of k k prime. Then next lecture.
Yes, sir.
Okay, got it? Any question? So any problem? So everything will be calculated from this f of k prime.